So it's a pleasure to introduce Xavier Cabre from Barcelona. And he was kind enough to put the title of his talk in the board. So I guess you know that I know how to read, so I will not read. I will not prove it to you. And I give I think you have to.
Sure.
Yes. So I'm going to start with the mathematics.
Okay. Thank you, Gabriela, for the invitation. It's a great pleasure. Many of you know Gabriela and I are mathematical brother and sister. She's a little older than me, but
you couldn't say, right?
So I didn't meet you in New York at
No, that's
true. But thanks a lot for the opportunity, especially to this great occasion that Lou is here, and we are celebrating this great prize for him. So I will speak about, I want to tell you some new works I've been doing on a concept that's called non-local mean curvature. So the title, as you see, is Curves and Surfaces with Constant Non-Local Mean Curvature, meeting Alexandrov and Delaunay. And this is a preprint in archive that you can find in archive from January 2015. Okay, so just to give a fast account, this concept of non-local mean curvature was introduced recently, like 3 years, maybe 4 years ago. I will tell you the main results about it. There are not too many still. In particular, it leads to a new concept of minimal surface called non-local minimal surfaces. Surfaces with zero non-local mean curvature. And this is the first paper, this and another one that I will cite in a second, are the two first papers on surfaces with constant non-local mean curvature, constant different than zero, okay? So this is an extension of the so many words that there are on CMC surfaces, constant mean curvature surfaces. Okay, so let me just start recalling what is the perimeter and what is fractional perimeter. Maybe it is a little too small. You can read.
Put out the lights.
Maybe.
Without the lights, yeah.
That's right. A little better. So as you know, if you have a nice bounded set in a Rn E, standard perimeter can be defined through duality and the divergent theorem, and turns out to be the W11 semi-norm of the characteristic function of E. So the L1 norm of the gradient of the characteristic function of E, right? So this is one way to understand perimeter through duality, and this brings to bound BMO, the BMO theory. So fractional perimeter, the simplest way to introduce is just taking the same characteristic function, and instead of the W11 semi-norm, consider a fractional, Sobolev fractional semi-norm. For instance, this one. And the fractional Sobolev semi-norms are double integrals, okay? Double integrals. You take the function here, you evaluate at 2 points, x and y, you subtract, and then there is always this kernel on the denominator here, and then dx, dy, okay? But this is just the characteristic function of E. Therefore, if x and y are in E, this is 0. If x and y are in the complement of E, this is 0. So this integral is just simply twice the double integral over E and over the complement of E of this function here, x minus y to the power minus n minus alpha. Okay, so this makes sense. In fact, this is finite if E is bounded and sufficiently smooth. So this is fractional perimeter, is defined in this way. There is always a constant here that sometimes I will forget about it, but you should keep it, since, for instance, if you make alpha 10 to 1, this converges to the classical perimeter. But for that, you need a constant here, okay? And sometimes this alpha, some people write it as 2s. This is also a common notation. Alpha equals 2s. We'll come back to this later. So I'm assuming always alpha between 0 and 1. This means s between 0 and 1/2, okay? Otherwise, this doesn't make sense. So this is fractional perimeter. And let me tell you, for instance, that there is an isoperimetric inequality, which is it's not difficult to prove with Schwartz symmetrization. And balls are the unique minimizers of fractional perimeter given a volume, okay? This is the fractional isoperimetric inequality. That was known by Lieb and Almgren and Lieb, that balls were minimizers. The uniqueness, that they are the unique minimizers. This is a not so old paper, so quite recent, 2008 by Frank and Xavier, okay? It's not difficult anyway. Now there is a quantitative version, quantitative Italian version, right? First by Nicola Fusco, Vincent Millot, Vincent is French, Morini. Then another paper, 2014, with Alessio Figali and Francesco Maggi. And in this paper, which is an archive, you can see nicely computed the first and second variation of fractional perimeter, because that's our duty now, to make the first and second variation of fractional perimeter. The first will be very easy. The second is not easy at all, and it's not easy to understand, and we are far from understanding the second variation, which guys are stable, which guys are not stable. So in this talk, mainly we are going to talk about the first variation. The first variation is this formula. So this is the concept of non-local or fractional mean curvature, non-local mean curvature, NMC. You have the set E. Maybe here could be unbounded, and this will make sense. You take a point X, but it has to be smooth, okay? At least for this definition. Say C2. But it may be unbounded. You take a point X on the boundary of the domain, and then the fractional mean curvature, and local mean curvature, is this quantity here. This is a principal value. And then you take an integral in Rn, dy, x is fixed, dy. You look at the distance of y to x, and you make always this power here in the denominator. And on the numerator, you put a 1 if the point y is in the complement of E, and a -1 if the point y is inside the set E. So just think this in polar coordinates. For every sphere, the red thing here, for every sphere centered at x, you just make you count the proportion of ones with respect to -1s in the sphere. And then after, you just integrate with respect to the radius of the sphere and this power of the radius, okay? So you're counting, for instance, the mean curvature here, the non-local mean curvature at this point seems to be positive. There are much more ones than -1. So just think in this way intuitively, and just notice that there is no problem of integration at infinity, because this is bigger than n, so at infinity this is integrable. And at x equals y, there is a problem here. But when y is close to x, if this domain is regular, locally looks very much like the half plane. So locally there are as many ones and as -1s, and there is a cancellation. And this cancellation makes this to be integrable. It's the principal value sense, okay? So this, in fact, reminds you, all of you who know about the fractional Laplacian, this reminds of the fractional Laplacian of a function. In fact, this would be the fractional Laplacian of this function, 1 minus 1, computed at the point x, when at the point x you put the value 0 for the function, okay? So let me just remind you very fast, because I don't have so much time, about what is the fractional Laplacian, where it comes from, but very fast. Well, the fractional Laplacian is the infinitesimal generator of Levy processes. These are like random processes like Brownian motion, but where the particle can jump, okay? So when you are at a point, you can jump anywhere in the space. For instance, discretize the problem, imagine an integer lattice with very small size. You can jump to any point at a given time with a certain probability that will be smaller for points which are farther away and greater, bigger when for points, the closest points, okay? So you just ask yourself, what is the probability of being at x at some future time, t plus the increment of time, and this must be condition probabilities. At the previous time, you had to be wherever in space, in the lattice, wherever, and this is the probability of jumping from this point to that. You write this, you subtract the value at t, at x at time t, and you see what you get, an increment in time, and here like a Riemann sum. And if these probabilities are like power decays, power decay at infinity, like this, then this is a Riemann sum of this integral here. And this is the definition of the fractional Laplacian at the point x at time t. So forget about time now. The fractional Laplacian at the point x is, you look how much you are at the point x, you subtract the value of your neighbors, say, but all neighbors, ux plus y, and the ones which are closer count more, and the ones which are farther count less, and you integrate. And this is the fractional Laplacian. You already see the maximum principle coming here, so we are in safe hands, like as we would say. Yes. Because if the function has a maximum at x, this is going to be positive, okay? If the function has a maximum at x, this is going to be positive. And also you can symmetrize this, changing y by minus y, and making the average, and you get this expression. And this is very nice because this is a second order increment. So you see right away that this is like a generalization of the Laplacian, which would be the infinitesimal limit of this. But now I'm not making a limit, I'm making an integral, but the points which are closer count more. Okay, so this is a fast introduction to the fractional Laplacian. Okay, and let me just say that there is an integration by parts. If the function u decays at infinity very fast enough, you can make sense of this, and integrate by parts and throw half of these derivatives to the other function. And then what you get is the HS semi-norm, which is this, the HS semi-norm, which looks like fractional perimeter, right? But for this to be defined, you need u to decay a little fast at infinity. Also, Fourier transform, the symbol of the fractional Laplacian is this one by Fourier transform, okay? So let's go back, let me just go back again, remind this definition, okay? This is the definition of non-local mean curvature at the point x. Okay. So if the domain, okay, so you want to say that a plane has zero non-local mean curvature. If a plane doesn't have zero non-local mean curvature, we are in bad shape. Okay, the expression makes sense, but you would also like to have the concept of minimizer. Is it a minimizer or not? For that, a plane has infinite area. So how do you define it to be a minimizer or local minimizer? You have to work in compact domains. So this is the candidate, say, to minimizing fractional perimeter, this blue set E. It's going to be a minimizer if for every compact domain, omega, it is a minimizer when you fix the boundary values. But here the boundary values are the exterior values of E. So all this is fixed, all this is fixed. Competitors must agree with E here and there, okay? And they can change inside. So this is the competitor here in black. And then the energy is the one that we saw in the first transparency. The energy, of course, must be this, okay? Points inside with points outside. But if you just consider all the points, you are lost, because this will give you infinity. because you can run away at infinity and will give you the same many, many times. So, but these ones are common for all competitors, so you don't consider them. And then you just consider these couplings. Inside, say outside, so in omega and in E, and not in E but in omega. In omega and in E, but not in E, and outside omega, this part here. And not in E but in omega, with in E but not in omega. And you just forget the neither in E and omega, neither in, well, in E, not in omega, not in E, not in omega. Because this is common for all competitors. This is the right functional, and then this is, again, this is the Dirichlet data is the value outside, okay? Not only on the boundary, but all given outside. And this fractional perimeter and the non-local mean curvature, which is the first variation, was first introduced, so 4 years ago, say, by Louis Caffarelli, Jean-Michel Roquejofre, Vivius Sabin. And when the mean curvature is 0, it's what they call non-local minimal surfaces, okay? So, well, this is a motivation, but I'll skip this because I don't have so much time. So this is another formula which is nice to keep in mind, sometimes it's useful, for non-local mean curvature. Instead of an integral in Rn, you can write the value as an integral over the boundary, just using the divergent theorem. X is fixed, y now runs on the boundary of E. I mean any dimension, E is in Rn. Y runs on the boundary of E. There is always this kernel, and then on the numerator there is the angle or the scalar product of position with respect to X and normal at Y. So you see, if the domain goes convex, this scalar product will have a sign, perhaps, and then if it turns and becomes concave, it will have the other sign. So in a way, it's like capturing curvature, but in a non-local way. Okay? But in this talk, we use only, in this work, we only use this expression. In other words, this is useful also. Okay, the simplest examples, a hyperplane, of course, hyperplane has 0 non-local mean curvature, and in fact it's a minimizer, because at every point on the plane, there are as many 1s and minus 1s, of course. A ball has constant positive mean curvature, because at any point on the ball there are more 1s than minus 1s, right? And all points on the ball are on the boundary of the ball are the same, so it's a constant, of course. And this is a new thing with respect to classical mean curvature, as we will see. A band in R2 is an interesting object already, this band, because the boundary has 2 parts. If we were talking about classical mean curvature, you would say that this has 0 curvature and 0 curvature, but not here. Here, a band in R2 has positive, constant non-local mean curvature. Because if you take any point on the band, all of them are the same, so let's take this one. You make a sphere around it. There are more 1s than minus 1s. And therefore, then you integrate on the radius of the sphere, remember? But this will give you a positive constant, which is independent of the point, so it's a constant. It's the simplest, these two are the simplest CNMC sets, constant non-local mean curvature. Okay. Well, I have to go fast. About 0 non-local mean curvature, there are nice results already in the paper by Caffarelli, Roquejofre, Sabin, existence of minimizers, a density theorem. Maybe the latest theorems are like these ones by Alessio and Enrico. It says, if you know that the minimizing non-local minimal set, so I'm always speaking about minimizers, is Lipschitz, then you are fine and it's infinity. So cones, for instance, are always, like in the classical theory, are the are the obstruction or the enemies for regularity. But the cone is not Lipschitz, okay? If you are Lipschitz, you are infinity. And then this is the complete result in R2. In R2 is the only dimension where we know everything, thanks to this paper by Ovidio and Enrico. In the plane, any global minimizing non-local minima set is a half space, in the plane, a half space, okay, a half space. So in particular, all local minimizing non-local minimal sets in a compact domain are C infinity. You prove it after having this D theorem, okay? Note, for instance, in the plane, this guy has 0 non-local mean curvature. If you, or think of this one, this is simpler, but also this, if you go take any point here, if you count the number of ones and minus ones, is 0, because everything is symmetric with respect to this line. So they cancel. So it was a candidate, and this paper, which is a very nice paper and it's not trivial, says this guy is not going to be a minimizer. And then there is another nice paper in arXiv by Juan Davila, Manuel Del Pino, Junxian Wei, when they start studying, well, first they find some classical, this is not anechoic, this is catenoid. I made a mistake here, sorry. For instance, they find a new object which is the replacement of the classical catenoid. They call it the non-local catenoid, and it's something which has the same topology as a catenoid. It has constant non-local mean curvature, but it doesn't go logarithmic like the classical catenoid. It goes as a power. So the asymptotic behavior is very different, but it looks the same. This guy is in general is not a minimizer. And then they start studying cones, Lawson cones, and things like this, maybe not circular. Already in R3, you can imagine a cone which is not circular, okay? You give a curve in S2 and you produce the cone. This we still don't understand if they are always unstable. We suspect that they are always unstable, but there is no theorem like this, okay? So they start proving that first there are with 0 non-local mean curvature, and they study a little the stability for the circular ones, okay? What is missing is Simon's lemma saying no cone up to dimension 7 is unstable. No cone is stable except the plane, the hyperplanes, which is, this is what we don't know how to prove, okay? But circulars, maybe soon we will know everything, circular cones, but it's not so difficult. But even that, you have to put it in the computer because there are always a hypergeometric functions and all this, okay? So this is the remaining question. And now we come to non-local surfaces with constant non-local minimal surfaces, okay? And let me remind you, in the classical case, the two most basic theorems probably are these two, not in chronological order. Let me start with the Alexandrov theorem. If a nice set has a boundary with a constant mean curvature, classical mean curvature, and it's bounded, this is very important because if not, the cylinders, there are the cylinders, if it's bounded, then it must be a ball. This was proved by Alexandrov, 1958. It's the first time when the reflection principle and the moving planes method was used and developed by Alexandrov. And then, but before that, there was another theorem about constant mean curvature surfaces, the one of Delaunay. I didn't know that in 1841 there was already the Journal de Mathématiques Appliquées. In R3 and also in Rn, n greater or equal than 3, there are, besides cylinders, straight cylinders, there are periodic, we call them periodic cylinders or Delaunay cylinders, periodic surfaces like these, with the topology of the cylinder, say, which have constant mean curvature, okay? Here, both curvatures are positive, this one and that one, but they are not too big. Here, one curvature is positive, one is negative, but the one that is positive is so positive that kills the negative and makes the same value as here, so it has constant mean curvature. And they are produced in this way. For instance, in R3, you roll an ellipse through a line, trace the focus, and this gives you this curve, which is called the envelope. Okay. So what I want to explain is this paper by myself, together with Mustafa Fall in Senegal. Mustafa Fall was a student of Andrea Malchiori, and then was in Frankfurt with Tobias Weth, doing a postdoc. So Tobias Weth in Frankfurt, Mustafa Fall, and my colleague in Barcelona, Joan Sola Morales. Okay. And our first theorem, this is the first theorem in CNMC surfaces, okay? It says if you have a bounded, nice set, and its boundary has constant non-local mean curvature, alpha is always fixed between 0 and 1, then it must be a ball, okay? And we find this theorem at the same time as Shiraolo, I don't remember his name, his first name now, Alessio Figali, Francesco Maggi, and Matteo Novaga. We got in contact and we put it in archive the first day, the same day, because we did it completely independently. But in the paper, they also have a quantitative version. So in this, with respect to this theorem, the result is stronger. It's very nice quantitative version that says if the non-local mean curvature is not constant, but it's almost constant in the sense that it's the Lipschitz norm on the boundary of the set of the non-local mean curvature is small, then you can trap the set between two balls which are with almost the same radius. So in fact, this is very, very strong. This is much stronger and much easier to prove than in the local case, in fact. So these equations are very rigid. They bring you to symmetry much faster and much easier than the local ones. And you will see it in a while because this theorem is very easy, quite easy to prove, in fact. And my favorite, anyway, is the Delaunay one, that this is what we prove also in this paper with Mustafa, Joan, and Tobias. So we have these two theorems. Instead of looking here, let me just look at this picture. What we prove is that from a straight band that has constant non-local mean curvature, a family of periodic bands bifurcate. They are these red things. These are periodic bands, so they repeat, the same thing repeats periodically. The band is symmetric, so this is reflected with the minus. You see, this is a function, UA. A is this parameter, which is pretty much this height. This is UA, this is minus UA. And all these surfaces have constant non-local mean curvature. Okay? Even in the plane, these guys exist even in the plane. Okay? Sorry, now we'll see a picture. But their periods are different. But you can make them converge to 2 pi if you choose this height well enough. And the same holds in Rn and greater or equal than 3, but this is another paper because all these things are quite technical to prove, as you will see later on. So the theorem says this: in dimension 2 there is a radius and then a family of functions. So just small parameter, it's a small perturbation result, okay? With the implicit function theorem. And these sets have all same non-local mean curvature. They converge to the band as A goes to 0. They are all different, and their periods go to 2 pi if A goes to 0 and R is chosen appropriately. This is the band with radius R. Okay. And this is the picture we computed them with MATLAB. This is not very good, but this is robust. It's really like this. And this is how they look. The bandwidth we here, they are very much up. They spend a lot of time, say, above the average and less time below a certain average. They look like this. And when A is larger, they look like this. And here you see the different periods. I think the period becomes smaller as the amplitude gets larger. Okay. I'll skip this. This is a semi-linear stuff, periodic solutions that I do with Joan. Let me just mention very fast the proof of the first theorem. You use the reflection principle of Alexandrov. You use the reflection moving planes method. This is the domain E. You start moving the plane, you reflect E, and you consider E lambda. This is a nice situation where the reflected cap still contained in E, and you keep moving the plane until there is an obstruction. As you know, the first obstruction is that the cap, the reflected cap, touches the set E at an interior point. And then you have this picture. And then you use your equation and you say the mean curvature of non-local mean curvature of E at the point X and at the point X lambda is the same. But the mean curvature of E at the point X is the same as the mean curvature of E lambda at X lambda, of course. So you have two sets, E and E lambda, that have the same non-constant mean curvature at the same point, X lambda. And now you just look at the definition of non-local mean curvature. Remember, it's an integral. Some points go with 1 and some points go with -1. The points that go with 1 for this and for E lambda and for E will give the same contribution here and here. For instance, these ones, the ones in these two caps here, they are both, I think, -1. They are both -1 for E and for E lambda. The points outside of everything are 1s, both for E and for E lambda. So they give the same contribution. The ones that remain are these 4 sets, this one, this one, this one, and this one. But at every point here, it's very simple to prove, huh? You just have to think about it 1 second. At every point here, this gives for the point E at the point X lambda gives a -1 when you compute for E, and a +1 when you compute for E lambda. And the same here and here, but the distance is always larger from Y to X lambda than from Y lambda to X lambda. And this makes a contradiction right away when you see both integrals. They cannot compare, but right away. So that's a proof. The maximum principle is inside this argument. Yeah, the definition. And this brings to a quantitative version also that Chiraolo and all proved. Okay, but we just do this. Well, the second obstruction, as you know, it's a tangency. Okay, and then we prove a new formula for what is the directional derivative of non-local mean curvature through a tangent vector to the surface. V would be a tangent vector to the surface boundary of E, and you have to compute you have to prove this formula, and once you have this formula, pretty much is the same as before. Okay, I don't do anything, but it's just like this. But it's okay, it comes back. So this is theorem 1, but my favorite perhaps is theorem 2, okay, because it's a little more involved, and this is the Delaunay theorem. We use the implicit function theorem after Lyapunov-Schmidt reduction. I have to be a little fast. Let me go a little fast. This is, I'm doing everything in R2. The sets look like this. So there is a function of one variable. I like that. Function of one variable, okay? I like that. And then this is the reflection. And I use Fubini to compute the integral of 1s and -1s. I use Fubini and I integrate first on every vertical line. And this is very easy. Lemma, you prove a formula for the non-local mean curvature at this blue point here, SUS. And integrating after this and applying the divergent theorem, you get a contribution from this point and from this point. And these are these two terms. And this one gives you this term. Capital F is a nice hypergeometric function which is like this: bounded, odd, concave, convex. It's just that. And here you have f computed at the increment, first order increment of the value of this value of u here and the value here. This is the point s minus t here. And then the typical kernel for the fractional Laplacian. But this is non-linear on u. And this here with a plus, this is new. This I had never seen before, this is a plus. The plus comes from the interaction of this guy with these ones here. And u of s minus u of s minus t is minus and minus, it's a plus. Okay? If f was the identity, this is the fractional Laplacian of a certain order, of a certain derivative. If f is the identity, this is the fractional Laplacian. This is not the fractional Laplacian. This may look quite bad. This looks bad when t is 0. There is no cancellation here when t is 0. But when t is 0, this is positive, because u is positive. This is very small when t is 0, so this goes to infinity, and it cancels with this thing here. So it's very smart. You just do the computation, it's very easy, but it turns out to be very smart, and everything is fine at the end. And this is a functional now that I call of non-local, quasi-linear type. And I call it quasi-linear because it's non-linear on the first increment or first derivative, say, in a way, okay? And this is what we want to make this equals constant for a curve like this, which will be periodic and close to a bound. The first thing you do, I learned this in Ambrosetti, in the book of Ambrosetti and Prodi many years ago, is that since you don't know what is the perimeter, it's very important to leave it open. The perimeter has to be free. If you fix it, you are in bad shape. I mean, you don't know what it is, leave it free. But rescale variables to make it 2 pi, for instance. And in this way, I will work among functions which are 2 pi periodic, and I will have a functional space. So you do that, you rescale variables. It's not written here, it's written here, rescale variables to make now the function periodic of period 2 pi, but the functional will change. The functional will change, and let's look directly here. The functional changes because, the plus infinity becomes 2 lambda r over t. Lambda is the period. Lambda is the period. This also changes. This is because of the scaling, nothing else than that. And then there is a trick, Randall-Rabinowitz type trick, which we have to divide by a, otherwise we could not apply the implicit function here, but it's just a trick. Remember, a is the small parameter, which is the deviation from the band, okay? And the solution, you look it like this: constant r, after rescaling constant. The first contribution for a 2 pi even periodic function is the cosinus. And then comes the cosinus 2s, cosinus 3s, cosinus 4s, cosinus. So you make explicit the coefficient of the cosinus, the 0 order, and the rest is from cosinus of twice the angle, cosinus 3 times the angle, 4 times the angle. Okay? And this is the equation now. And already now I want 0. So this means constant on local mean curvature. Okay? And let me just show you, well, the spaces you work with 2 pi periodic even functions, 2 pi periodic and even Holder spaces, x and y Holder spaces. The functional is like that. A, you are going to linearize about a equals 0, so you should make already the value at a equals 0. And this you already get a linear operator because I divide by a, and this is the important linear operator. This is pure fractional Laplacian. And this is a convolution term. These are 2 terms, maybe, 2 terms here. But this term is a fractional Laplacian. And these are 2 terms, convolution type. For instance, this one, convolution type of the function with this kernel. Let's just go to look at it here. This is the operator. The first term there is a zero-order term, constant here, and the other is a convolution. Look at this. Maybe we don't have that much time, I'll write it here. This is the important thing. All the cosinos, k equals 0, 1, 2, 3, 4, all the cosinos are eigenfunctions of this guy with a certain eigenvalue. So in fact, I'm going to diagonalize the operator. And here something which is trivial, but I was not aware. If you have a convolution operator with any even kernel, this kernel here is this guy. Convolution with an even kernel, the cosinos are eigenfunctions. Why? Because imagine here cosinos of the difference, okay? It's cosinus of s, cosinus t, minus or plus, I don't know, plus sinus s, sinus t. But sinus t against something which is even on t gives you 0. So it goes away. And all what you get is cosinus s, cosinus t. Cosinus t, the cosinus s gets outside. And you just get a constant that will be the eigenvalue pretty much. And cosinus s, so it's an eigenfunction. And the same for the fractional Laplacian. So the cosinos are eigenfunctions of this guy, and of this guy. And you compute the eigenvalues, and we can compute them not explicitly, but we can prove that there is one which is the first one that corresponds to k equals 0 is negative. The first one is 0, danger. And all the other ones are always different, increasing, going to plus infinity. And they go like this, like k to the 1 plus alpha, which this is very important with Fourier. This gives you the invertibility and that you are in the right Sobolev spaces, or, well, we work in Holder spaces. This is by Fourier if you think it's the right number of derivatives, okay? And these look dangerous, and I will finish pretty much here, but you still have the derivative, and this was probably before, yeah, here. The derivative of the functional with respect to this parameter lambda, which was pretty much the period. And if you make the derivative of this with respect to lambda, lambda is always only here, and you get the cosinus, in fact, because you are linearizing around the cosinus. So everything, yeah, which was in the kernel, but here you get it in the image. So, yeah, so you cover everything, everything is one-to-one, and then you invert. And then there is another lemma which is like 15 pages because it's painful, but which is that you have to prove that this functional is C1 to apply the implicit function here. And this is not so, well, it's technical, but gives a lot of work. Already in dimension 2, in dimension 3, it's another paper because it's really painful. And the functional looks like this. This is that function f that I wrote before after some modifications, but pretty much it's a nonlinear version of the fractional Laplacian. And to prove that this sends a Holder space to a Holder space, okay, first you have to see that the image is bounded, then that it's in the Holder space, then that the differential is continuous from a Holder norm. Whenever you have Holder norms, it's quite painful because you have to always make difference and all this. So it's quite a lot of terms. And the trick here is to F1 is 0 when Q is 0, yes. So you take out, you factorize one factor here, you take it out, and you consider a new function, and then you symmetrize this, as I say, changing t by minus t, and you get here the fractional Laplacian times something which will be nice, say, and you work with this expression. Okay, and I have to finish here, but this was the end. Thanks for listening.
Thank you, Javier, for a very nice talk. Are there questions? Comments? Yeah, make a little if I may. Nobody? Ah, sorry. Stand up.
So you define a non-local perimeter with this alpha between 0 and 1. Is there any sense to do it for fractional, this fraction bigger than 1?
Yeah, alpha between 0 and 1 corresponds to S between 0 and 1/2 when you think about the fractional Laplacian to the power S, 2S derivatives. And what happens is that if you define this, that you can, when alpha is bigger than 1, that means, or equal to 1, which means S greater or equal than 1/2, well, you cannot define it with those integrals, but you could define it through an approximation, say, for instance. What you get in the limit is a classical mean curvature, okay? So to get a new, this new object, you have to be between 0 and 1 derivatives. Well, I mean, yeah, 0 and 1 derivatives. S less or equal, strictly less than 1/2.
Just a side comment. The last part where you seems to go to a great pain to apply the implicit function theorem. Why don't you try? Why don't you?
Is it working?
Is it working? Yes. Why don't you try maybe some degree type? You just get estimate degree type.
Non sentiamo.
Dice on. Okay? Works. So not just, I mean, maybe a naive comment that Xavier told us what a great pain he had to go through to apply the implicit function theorem at one stage. And so since nobody likes pain, so I was suggesting maybe implicit function theorem gives lots of information, of course, but maybe since you are after existence, maybe one can try degree type argument. To have the estimate, try to deform with your parameter and show that, say, for equal to 0 degrees differ from 0. And sometimes they go together, the two examples. I don't know.
Well, we can try, but for sure it should work. I think it should
I don't know
work.
if it works.
And it could be useful perhaps to go for, because here we just get the small
Yeah, to continue.
cylinder
To continue.
actually.
As long as we have good estimate.
It could be useful to get a larger. And also it would be nice to get these guys from a variational
Also, yes.
point of view, but it's not so clear how to do.
Peter also.
Naive question on the fractional Laplacian. Is it interesting to consider different kernels decaying not like powers or maybe non-symmetric? Does it have any interest in motivational point of view?
Yeah, for instance, compact support kernels are interesting and have been considered. Okay, all these equations in the piece paper by Fusco and company, the first and the second variation, in fact, is computed for a general kernel. Okay, the concept of non-local mean curvature.
More difficult if you're non-symmetric.
I've never seen it, but there should be an isotropic version, for instance, could be interesting, right? An isotropic version, and this would correspond to a general kernel, maybe singular, but not symmetric on the
Free cancellation.
Yeah.
Other questions? Yes.
Let me take you back to the...
Speak loud.
Stand up. Say that.
No, but speak loud.
Yeah, because
Okay, let me go back to the very classical facts from 60s and 70s, from the minimal certainties, right? So all these stems from this initial paper by Caffarelli, Joffre, and Savini at the beginning. And this replicates this initial approach of De Giorgi,
Yes.
minimal cones and blow-up methods, right?
Yeah.
And then there's this other theory which is connected to non-uniformly elliptic operators. This means that we take a special structure, imaging a P Laplacian of P equals to 1 plus special structure, and then we rewrite things on the graph so that we get the Laplacian.
The A operators.
Yeah, exactly, the A operators. Do you think there could be, because this is, let's say, this is the parallel of the beginning, but there could be more. I mean, do you think there's an analog of that I mean, which parallels these recent developments of non-local, non-linear fractional operators? Because this could be also interesting.
I think, okay, the A operators can be like the fractional Laplacian isotropic,
Yeah.
but then could be also an isotropic, right?
Yeah, exactly, right.
I think this goes in the same direction that Italo was saying, considering a general kernel. First, if you want symmetry.
No, because these you write them on the graph themselves, and then this becomes a Laplacian on the graph surface. So it's like a P Laplacian, but for P equals to 1, so it's non-linear. So it has nothing to do with the kernel. So it's like you minimize the m, it's like this old functions where you minimize the m root of 1 plus the gradient to the n. And there's a whole literature going on that, right? So this is something in between this fractional P Laplacian with P going to 0 plus structure that makes them related to minimal surfaces. So do you think there could be developments in that way?
Well, I should think more about what you're saying. But probably, do you think would be something like this, but here with a kernel, depending on T, which is not a power?
Depending on you.
On the graph.
That's what I'm saying.
On the graph. I see.
Because that's the very classic.
Well, okay, this F is this F simply because I took that kernel. Okay?
Yeah, exactly.
If I take another kernel, you'll get another function here, and probably also could be an isotropic.
Yeah, that would be also interesting to go in that direction.
Yeah.
Right.
So this should be the extension of what you have in mind.
Probably,
Doing
right.
this computation
For
another kernel.
Yeah, exactly. For another equation which is non-linear depending on the solution. That's the one. Take the following function of m root of 1 plus gradient to the n. So this has linear growth. And take the equation which the Euler Lagrangian which is non-local.
The solution as a graph.
No, because there's a huge literature, but this came after these approaches of the Jones. There should be probably a parallel.
Okay, yeah, I understand what you mean. Instead of a square, maybe something different. Yeah. So there is a lot to,
A lot, yeah.
But still we have done pretty well.
something.
Okay, so thank you, Javier, and maybe we'll try to move on to the next talk. We are already